Yes, hi everybody. I am Melina Veneziani. I am a scientist at the Los Alamos lab, and I mostly work within the water cycle and the cryosphere teams. So the study that I will present today is mostly the work of Hyein Jeong. She used to be a postdoc at Lano until about a year ago, when she moved back to South Korea, and she's now a researcher at Hyein University. So she's been working on basically looking at dense and bottom water formation in the Polynyas that are represented in E3SM high resolution simulation. This is part of a manuscript that has already been revised, and it's now in a fairly final form. And she's planning to resubmit it to the Cryosphere journal. And these are the co-authors of this paper. So a few words of background first. So what are Colonies exactly? So they are areas of open water or very thin sea ice. So ice that is thinner than about 20 centimeters or so. It's open water surrounded by either the winter sea ice pack on all sides for open ocean Polynyas, or open water surrounded by winter ice pack on one side and the coast, the continent, on the other side. And these are the coastal Polynyas. So this is just a figure to show from a paper, fairly old paper from Harigo and Van Dyken, where that shows, it's a nice picture that shows all the coastal Polynyas in Antarctica. And also I added the open ocean Polynyas that are sometimes observed. So there are two Polynyas in the Weddell Sea and the cosmonaut Polynya in East Antarctica. So why do we care? So Polynyas are important for formation of the densest waters in the ocean. So they are very important for the meridional overturning circulation and the overall transport of heat. They're important for carbon sequestration and also biological production. So just to give you a little bit of an idea about the processes, in the coastal Polynyas, the main mechanism is atmospheric winds. So the main driving mechanisms is the strong burst of katabatic winds that come out of the Antarctic continent. They can also be found in the Arctic. They're not just a Southern Ocean feature, but we'll mostly be talking about the Southern Ocean in this talk. So these strong winds come out of down from the continent. They push the newly formed sea ice away from the coast. And then the water that is left there basically continuously forms sea ice because it's cold enough. So there is strong latent heat exchanges with the atmosphere. Sea ice keeps being formed and pushed away. So there's a lot of brine formation in the ocean. And so you had the formation of this very dense, cold, and high salinity waters. That's basically Antarctic bottom water. The open ocean Polynyas are different because they are actually the driving mechanisms is in the ocean. So the ocean initiates for some reason that depends on the situation, but a convection, a deep convection cell. And this convection in the ocean brings up the relatively warm and saline waters that are the CDW in the CDW in the Southern Ocean. So this water gets in contact with the atmosphere. It doesn't allow the sea ice to form around it. There's a strong sensible heat fluxes exchanges with the atmosphere. And also there's a positive feedback because you bring saline, denser water to the top. So these are the two main mechanisms for these two different polynyas. So this is the outline of the talk. I'm going to present, I'm going to show you how E3SM high resolution and also a little bit E3SM low resolution, how they represent coastal and open ocean polynyas. Then Hyein looked at formation of dense and bottom water, mostly in E3SM-HR, associated, so the bottom water associated with the model polynyas, and then there will be some conclusions. Okay, so coastal polynyas first. These results are from E3SM-HR only. They show basically in the first panel, there is latent heat flux exchanges with the atmosphere. So it's positive going because it goes mostly into the atmosphere. And then on top of it, it's winds, so surface winds. And then the second panel shows the sea ice production during the freezing season. And so you see that there are these very high values near the coast and in these regions that are basically the main coastal polynyas. And they are also associated with the strong winds coming off Antarctica, and they're not easy to see, but there are very small areas of high latent heat flux exchanges. There is also a comparison of accumulated sea ice volume in the coastal polynyas between the model, which is the pink curve, and this is a satellite observational product in gray. And you see that typically the model does fairly well. There are only some polynyas where the model sea ice production is not as high as in the observations. Yeah, so I think I said that. Now, to look a little bit more specifically about each polynya, this is a plot of volume for each polynya, sea ice volume versus sea ice area for each polynya from the E3SM-HR simulation in red, the low resolution simulation in blue. I believe this is the low res tuned HR simulation, and then observations in gray. So what you see is that mostly, so E3SM low resolution doesn't do a good job at all. In some cases, there is no polynya whatsoever. And that's expected because it's low resolution. But the high res does a pretty decent job in most of the polynyas, except for 4 of them, and where basically there is not much difference, and they correspond with the polynyas that where you would see a different sea ice production in the previous slide. And so one hypothesis is that these polynyas are usually formed in the real world against landfast sea ice, which is sea ice that is anchored in a sense against the land. And so we are not reproducing landfast sea ice yet in E3SM. So we're really not giving a support for the polynya to form. Okay, so open ocean polynyas. There are many that are formed during this, the very short time of this run, and there are 3 different types. So they're mostly, so you can see that there are mostly. This is the Weddell Sea polynya. This is the mud rise, which forms at the mud rise seamount. And then there are years where you have both of them at the same time, or where you have the formation of this, what we call embayments, because they're really not polynyas. They're really just big gulfs of sea ice free area. They're not really surrounded by sea ice on all sides. So there is an enormous amount of convection going on when there are these embayments. So in reality, I should say that since we have had satellite observations available, we have only observed a few instances of motorized polynyas. The latest one was in 2017, and then a big Weddell Sea polynya in the 70s. This is just a plot that shows basically the classification of the polynyas. So the model reproduces these polynyas at a rate that is a little bit perhaps more frequent than what we see in recent observations, but this is not something that is specific to E3SM. I've seen other models that do the same thing at high resolution. Okay, so Hyein then looked at deep and bottom water formation for the two different, coming from the two different polynyas. She utilizes a framework that's called water mass transformation in oceanography. And it's basically and this is just from, so transformation that is just due to the surface fluxes. So surface flux exchanges with the atmosphere and with the sea ice. So typically I just wanted to show you a formula here to give you a little bit of an idea. So this would be the WMT that will be plotted in the next slide. It's in Sverdrup, which means it's volume per second. And it's basically how much water is formed, is transformed from density sigma k to sigma k plus 1, just due to surface fluxes, not internal mixing. So, so this is the density bin that you can vary from a certain initial density to the last density. And then there is, this is just the heat flux exchange, which is mostly heat flux exchange with the atmosphere. And then there is a freshwater flux that is due to both the exchange with the atmosphere and also exchange due to sea ice melting and forming. So sea ice forming is basically brine rejection into the ocean. Okay, so this is the main plot. And I would like you to focus on the right-hand side, actually. So typically, this is the water mass transformation rate in Sverdrup as a function of density. So if this is positive, it means that the density of that water in that bin of density is becoming higher. So it's becoming less buoyant. If it's negative, it means that the density is becoming smaller. So it's becoming, that water is becoming more buoyant. Okay. So the black curve represents the overall in all the Southern Ocean, the water mass transformation rate in all of the Southern Ocean south of 60 south. And this is for the winter, for the winter season only. I believe it's March to October. So I added some values for, so this these waters with these densities are lower CDW and Antarctic bottom water, so the densest waters. Then there is upper CDW, which is still dense water, but it's above it, above the bottom water. Then there are intermediate waters, and then the surface and mud waters that are basically above 500 meters, I would say 700 meters or so. Okay, so and then what she did was to calculate the same quantity, but for the Weddell Sea region only. So that would be representative of the basically the convection that is happening in the OpenOcean Polynyas and in the coastal shelf, so the green one, the green region. So that would be representative of the water that's formed in coastal Polynyas. So what you see is that the densest water masses that form at 28.2 density are mostly happen in the open ocean Polynyas, not in the coastal Polynyas. And this is different from observations. She also did you can also kind of separate what is contributing to the water, what flux is contributing to the water mass transformation rate. So the total is this black line. So this is due to the continental shelf. This is the open ocean Polynyas. And then the blue is due to the sea ice formation, and the red is surface heat flux. So what you see is that in the open ocean, in the Weddell Sea, where you have this Antarctic bottom water formation, things work as expected, in the sense that you have mostly the water formation due to exchanges of surface heat flux inside the open ocean Polynyas. But what is different is that than what's observed is that on the continental shelf, we don't really get bottom water. We only get upper CW and intermediate water due to brine rejection mostly. So why? So we looked at a number of things. We looked at hydrography and stratification on the shelf. So this is a plot of density at the surface from the WA 18 climatology and from E3SM-HR. So you see that while offshore we are doing very good, near the coast we are so it's too low, the density. Okay, so it's too light. And why? Because it's too fresh. So this is a plot of sea surface salinity at the top, different with the SOSI climatology. And this is instead a seafloor salinity difference with respect to an observational product, Schmidt-Kuhl observations. So in both cases, you see that we are too fresh. So the ambient shed wall shelf water is too fresh to begin with, too buoyant. Not sure if I have enough time, but she also looked at how seasonally SST and SSS change. And so as you can see, and then compare the E3SM-HR with SOSI and WA. And so you see that in all season except summer, we tend to be fresher and a little bit colder, but in the summer, these differences are higher. Okay, so Hyein also looked at freshwater flux into the ocean due to sea ice melting only, and again from SOSI and E3SM-HR. And you see that this component from the sea ice is higher, much higher actually than SOSI. Now SOSI is a reanalysis product, so it's not the truth, but I think the differences are significant. And we also, if you look at sea ice thickness, it is consistent with the fact that we tend to have an accumulation of sea ice at the coast, especially during the late winter, early spring season. Okay. We also looked at surface winds, and they generally are stronger than the ERA 5 product, not only offshore, but also at the coast. This has a few consequences. The Weddell gyre circulation is intensified. If you saw here, this is much more intense than ERA 5, and this is an annual average. And so this is actually conductive to formation of OP. So that's probably one of the reasons why we get those more often. There's also enhanced Ekman transport from the stronger polar easterlies that are closer to the coast. So this could push sea ice against the coast. And then there is also an Antarctic slope current that is stronger than SOSI. Okay, and Hyein also looked at the vertical structure to basically try to look into more of this process. whether, you know, what is the strong Antarctic storm current related to, and we think that it is due to the stronger easterlies, sorry. So I'm not going to spend much time on this because I wanted to conclude. And so to basically say the story, we are able to reproduce the Polynyas, the coastal Polynyas and the OPs, but the densest water masses are not formed in the coastal Polynyas during the winter season. They're formed in the open ocean. And we think that this is possibly due to the fact that the shells are too fresh to begin with, and this is possibly due to an excessive sea ice that is accumulated against the coast, possibly due to wind and also stronger ASC current. Okay, so before concluding and going to questions, I wanted to show you some pictures that I think this picture is just amazing. It just shows the coastal Polynya in the Ross Sea and just how the sea ice is pushed away. I found this online. Of course, it's a NASA picture. And then the other thing that I wanted to show really quickly is this amazing animation that was made for the entry to the Supercomputing 21 Scientific Visualization Data Analytics Showcase by a team of Llano and University of Texas at Austin scientists. Mark was involved and a number of other people at Llano as well, a student, postdocs, Andrew, and so I thought it was really nice, and I just wanted to show. So this was there is a commentary that I have turned off, and this is E3SM-HR that was run for a few years just to save some fields at the higher frequency to make this animations. And there is I think at one, yeah, so here it shows the formation of the mud rice and Weddell Sea Polynya, which is, I think it's great. And then it also zooms in. This goes on for a while, but it zooms in to the coast and you know, shows some coastal Polynyas. Here is the Mertz Polynya, for example. And so I believe these are winds that you see on top, and that's sea ice, and yeah, and that's the coastal Polynya forming. I thought this was great, so I wanted to share it with you. So yes, so I am finished, and I'll gladly take questions. Thank you for listening.